Hi everyone and welcome to the new video. Today I want to show a very rare device that you probably never heard of. I myself never heard about this before, and this is the radiation meter from Philips. It is an extremely rare device and I am excited to make a video about this, and there is a simple reason for that. First, if I search on YouTube about Philips radiation meter, there are literally no links about this. And there is only one link about another model, and this video is 10 years old. So practically there is no information about this device. In this video I will show how it works, and I will test it with a real radiation source. Please be aware, this is an updated version of the video where I did the second part. So if you already watched the first one, just skip the first 10 minutes. And now let's get started. This meter was made by Philips in 1958, so it is more than 70 years old. And this is the very first generation of the transistorized radiation meters. Previous models were apparently with vacuum tubes. And this is a very beautiful design actually. It's a leather case, practically like an old travel suitcase. As you can see, it has a very nice click. Maybe I should make an ASMR video about that. Alas, the leather in a very bad shape. There is also a belt here, but it's completely disintegrated and it's split into parts, and I don't think I can repair it. Alas, this leather is very old and as we can see it is literally disintegrating. This box contains from two parts. Let me open it now. Alas, this part is also very fragile and it's a bit sticky. I am not sure if it can be repaired. If you know, please write in the comments below. And inside this box there were several accessories. One was a headphone or maybe a small speaker, I don't know. Second is a battery, and the battery is interesting. This is not a standard modern battery, this is 2R10 battery and it has a 3-volt voltage. As for this thing, I actually don't know what is it. It has a part number PW4014. I think it's just an adapter. When I opened it, there is practically nothing inside. Maybe it's an adapter for an external Geiger-Muller tube. There was also a document included. I am not sure if it makes sense today. There is no date on it. Apparently this document shows that this device is not used anymore. And let's see the meter itself. I will try to gently pull this from this box. As we can see, this design is interesting. Nowadays you cannot buy radiation meters in this format anymore. And this is 1957. And this is the device itself. As you can see, it's an interesting design from the 50s. It reminds a bit of Star Trek or something like this. As we can see, the maximum range for this device is 3 millisieverts per hour, which is pretty a lot. Interestingly, it's a sleek design and there are no screws at all here. As we can see, this top belt is broken and the previous owner tried to fix it apparently. I'm not sure if it's visible well on the camera. And we obviously see a Philips logo here. And here is the on and off switch. As I mentioned before, this device is using a non-standard battery that you cannot find today anymore, but you can find an adapter on eBay. As we can see, this battery already started to leak, so it was really nice that the previous owner removed the battery from the device. Now let's see what's on the top. Apparently one connector is for the speaker, so it should go like this. And the second connector has a GM logo on it. So I think it's for the Geiger-Muller tube, and apparently the extra tube can be inserted here, so it can be a long wire, maybe it can be on the rod or something like this. Now let's open the device and let's see what is inside. There are no screws, you only need to slide this thing from the left and from the right. There are no hidden screws, there are no glue or something like this. Alas, we don't see things like this today. As we can see, we have a meter and some electronics. At the top there is a Geiger-Muller tube. Let's open it. Now I remove the screws, and here what is inside. As we can see, it is a pretty simple design. We have a meter at the center, we have two transformers, we have a Philips Geiger-Muller Tube. The model is Philips 18503. Here we have one or two transistors. As we can see, there are not so many components inside. There are probably some diodes and capacitors, and that is it. This port is for an external Geiger-Muller tube. This port, as I showed before, was for the audio. Here we can install the battery, and as we can see, interestingly, plus and minus pins are connected to these screws, so I can just plug 3 volts to it and it should work. This battery is obviously dead for a very long time and it started to leak. I will not use it anyway. And now we're ready to turn the device on. But before doing this, I will show you the information I was able to find. First, it will allow us to better understand how the meter works. And second, it is important to preserve this information, because these links are old and they can be expired in every moment. At least this data will be in this video. This is important to preserve the history, because you know there is a well-known problem of the rotten links, because you know web hosting costs money. And for example, if this website owner stops to paying for the hosting, this document will just disappear. And as we can see, the first document is just a short booklet. It shows that Philips was doing equipment for nuclear physics and atomic energy. The scan quality is not very good, but we can see the description. As we can see, the device can be used for civil defense, for electron accelerator, for other physics tasks, like cyclotrons or something like this. Here we can also see some specs, like measuring range from 0 to 3 microrangens per hour. Interestingly, the lower power consumption and printed wiring were advertised as an advantages. In the 50s, PCBs were not common yet. It was a really new technology. So it is interesting to see this device. And the second document is a publication in the Philips Tech Review magazine, made in 1959. And this is a nice review, and it has a lot of technical details. And as we can see, 2 models were available. This is the model I have. And interestingly, it was mentioned that the original prototype was made in 1954. And here we can see the schematic, and we can see the idea of how it works. Here we can see a high voltage part. There is a transistor and the voltage multiplier. And then we have a Geiger-Muller tube and the resistor to limit the current. This module apparently transforming the pulses to a lower level. And this output shows information on the meter, and practically that is it. Here we can see a description of how the board works. If you're interested in the details, you can pause the video. And as I mentioned before, this is the only document available, so it's important to preserve this. Here we can also see a characteristic graph of the Geiger-Muller tube. And the working voltage apparently is from 4 to 600 volts. You are welcome to find this document online and read it. I think it is nice. There are also some suggested ways for improvements. And now let's turn the device on and see how it works. So out of the camera I just soldered these 2 wires. As we can see, the only thing I need to do is connect it to the plus and minus. This is fantastic compared to modern devices. I just connected 2 wires, to minus and to the plus. And here is the standard connector. Obviously I have no idea if it works. I'm using it the first time. We can also see the schematic in more detail. But in general, the schematic is in a good shape. I see no problems with that. I also have a radio code detector nearby, and I specially switched to a microrangens per hour mode, so it will be the same. I also have a piece of the uranium ore, and as we can see, it can produce about 2.5 millisieverts per hour, so this will perfectly match this range. Now let's turn it on and see if we can get something. And here I have a good news and the bad news. Good news is that there is no smoke. The device survived the first switch, and I am not sure if it's hearable on the camera, but I hear the high voltage noise. But the bad news, the device doesn't work. I can hear a bit of noise in the headphone, but there are no clicks. And as we can see, alas, it doesn't work. This is an on and off switch. This is the sensitivity switch, but there is no effect. I can try this port, but I don't think it will help. So here we can see the obvious result, the meter doesn't work, and now I will try to repair it. The schematic looks simple, so it should be doable. The only challenge is that some components are not available anymore. For example, this Philips Geiger-Muller Tube I was not able to find even on eBay, so I hope that this tube is okay. And now let's get into it. And because this device is a radiation meter, I will start from its central part, from the Geiger-Muller Tube. And the first test was interesting, the voltage on the tube was 0. And the reason was simple, this green diode at the left has a pretty thick wire, and apparently when the glue dried, the PCB trace was just broken. Interestingly, this broken trace already appeared in the video, but I did not see it at that time. So the first fix was simple, I just soldered a small piece of wire, and let's test it again. And as we can see, the result is interesting. Now the voltage is about 100 volts. It's important to mention that the Geiger-Muller Tube has a current limiting resistor, and this resistor is pretty large. Here it is 10 mega ohm, so practically we cannot measure the voltage with a standard meter, the value will be low. We still can measure the voltage, we just need to know that we must recalculate the values, there is a special formula for that. And as an example, I can measure the voltage of another Geiger-Muller Tube that works well, and as we can see the displayed voltage is about 140 volts, which is again not correct, but it is higher. So on this Philips meter, first I need to fix the high voltage part. By the way, this radiation meter has an input for an external Geiger-Muller tube, so I decided to also measure the voltage there. Apparently the current limiting resistor is located in the probe, so on the input we can measure the voltage directly. And as we can see, it is about 180 volts, still it is too low. Let's fix it. Now I will take the PCB out of the meter, and also I can check the schematic. And as we can see, the logic here is simple. This is the high voltage part. This module is providing high voltage to the Geiger-Muller tube. We have one transistor, one transformer, and the voltage multiplier, and there are 3 capacitors inside. I strongly suspect that these capacitors are not good anymore, because over time capacitors are degrading. And here I see 2 big capacitors near the Geiger-Muller tube. They look like a high voltage ones, because the nominal voltage is 700 volts. Now I desoldered one of the leg of the capacitors, so it is not connected to the schematic, and let's test it. And as we can see, the capacitor is larger than it should be, at 8000 picofarads, but what is more important, V loss is 6%, which is pretty high. These types of high voltage power supplies usually have high voltage but very low current, so the leak can definitely decrease the voltage. And as we can see, the second capacitor has the same problem, so I will replace them both. I don't have the exact capacitor like this, but I can easily combine them from 2 others. The voltage can be higher but not lower, and if you combine 2 capacitors in parallel, the value will be sum of them. And here you can see the replacement I made. This way I don't need to wait for a post-delivery, at least a week. Now let's test both capacitors again. This is the old capacitor. As we can see, it has a high voltage leak. And this is the new one, and as we can see, it is much better. Of course, there is another philosophical question. In old and rare devices like this, does it make sense to replace all the original components with new Chinese ones? It's not authentic anymore. There is no easy answer for that, but in my opinion, it's nice to see a device in the working condition. It's not like a museum, it's not under the glass, and it is important for people to see how these things work. But what do you think about it? Write in the comments below. And now I replaced both capacitors, and let's do another test. And as we can see, it is much better. I see 280 volts. And now I connected the speaker, and I can hear the clicks. The Geiger-Muller tube works. But as we can see, there is a second issue. I can hear the clicks, but the meter doesn't work. And even if I put a test source nearby, the needle is not moving, which is not right. Anyway, it's a good progress, let's go forward. Okay, at this moment the Geiger-Muller tube works, which is a good sign, because even on eBay there are no such tubes available, so it's almost impossible to find. And now I will take the oscilloscope and I will track the signal from the Geiger-Muller tube to the output. Let's get into it. I switched the probe to the X10 mode because the voltage is high, and here we can see the pulses of the background radiation. I will try to zoom it a bit. The pulses are relatively rare, this tube is not so big, it's not like SBM20. And the next component is very interesting. It's a germanium transistor from the 50s, a very early transistor technology. I can show it closer. It's even connected in the special socket. Maybe these transistors were very expensive, I don't know. Now we don't see transistors in the socket anymore. This transistor output has a low voltage, it's only 3 volts. And here we can see pulses as well. We can also see 2 other transistors. They apparently amplify the signal to a proper level that is required for the meter. I don't want this video to be too long. Out of the camera I checked other components and finally I have found the problem. Here on the schematic we can see 2 diodes, and from this diode the signal is going to the meter. And as we can see, in the middle point the signal is good. We can see it is amplified and good visible, but on the output of the diode there is nothing. So apparently this diode is dead and it should be replaced. By the way, as a test object I used this uranium glass ball. As the name suggests, this glass contains a bit of uranium and it is slightly radioactive. As we can see, when I place it nearby, the amount of pulses is increasing. And as we can see, at the diode output there is no signal. This diode is also germanium, so it has low voltage and I need to replace it with another germanium one. Luckily, it is easy to find them on eBay and there are lots of new old stock diodes that you can find. Out of the camera I soldered a new one. It's a much newer model and as you can see it is smaller, but technically it works. I also found another dead diode at the back side of the board and I replaced it as well. So these are the components I had to replace. And now let's do the final test. As I mentioned at the beginning of the video, I don't have the special 3 volts battery, so I will use the wires at the bottom to connect the power supply. And let's turn the meter on. And I see a good sign, the needle is moving. As we can see, the needle is slightly above the zero, this is the background radiation. I can put the test source nearby. I can hear the clicks. And as we can see, the needle is slightly moving. And I can switch the sensitivity to 10 times. And as we can see, the needle is moving, it works. Attentive viewers may wonder why the values are so low. In the beginning of the video I did a test with the radio code and the value was about 2 milliroentgens per hour. And here we can see only 0.2 or something like this. Well, the reason is that this meter is fully analog. It practically integrates the clicks using resistors and capacitors. There are no digital components inside. And as we saw in the video, this meter was made in 1958 and over the years all the components were degraded. They are not in the original values anymore. So to make this meter accurate, ideally I need to replace all the components, but practically I want to keep it as close to the original as possible, because nowadays it is more like a historical item. I'm not going to use it every day anyway. And as a funny note, in theory this meter can work even 100 years later, because components like resistors and capacitors can be easily replaced. But for example, the modern radio code will absolutely not working 60 years later. Over the years, all chips are degrading and there is no way to repair it. So this meter is 60 years old, but it is still working. But 60 years later, radio code's microcontroller will be completely dead. So as we can see, there are pros and cons of the full analog technology. And that is it for this video. As we can see, the meter works. If you enjoyed this video, press like and subscribe to see next videos. I have several other interesting meters for the test. You are also welcome to visit my Patreon page. The support helps me to buy things like this for testing. Thanks for watching and see you next time.